we looked at one consistency. We looked at two consistency. Is there a three consistency? Yes. So I'll just name it around and we'll not study that into a detail. So let's go A, B, and C, and let's give in some value RGGB, RGB. So it's completely consistent as it may appear. A solution is possible. Now, a three consistency, it checks consistency between three vertices at a time. So node consistency, what consistency checks one at a time. Arc consistency, two consistency checks two at a time. So three consistency will check three vertices at a time. I ask a question: if A takes a value V, then is there a combination of values for B and C from their domain that is consistent, that is possible? So let's do it intuitively. So if A takes in a R, is there a value for G and B? For B and C, yes, one can take B, the other can take G. On the other hand, if A takes in a value of G, is there a combination of values possible? Yes, it could take B, it cannot take G, but it could still take a R. So for every value here, I check for a combination of value between these two, which is basically you cross multiply their domain, so it becomes GR, GG, GB, BR, BR, BG, BB. You delete the values which are not possible. GG and BB are not possible because of constraints between B and C. And then you say for one value over here, do I get any value for the other one? So that's three consistency. Similarly, I could have four consistency. So I take A here and I take BCD here as a pair. For one value here, is there a combination of values of these three? Five consistency, six consistency, I could go all the way up to n consistency. I cannot go after n because there are only n vertices. How I make group of n plus 1 vertices when n exists? And not to a surprise, zero consistency is the weakest. Branches will still backtrack, it won't be able to detect. Two consistency is better, it has some prediction capability of branches that backtrack. Three consistency is much stronger, it predicts even better the branches which will ultimately backtrack. Four consistency is still better, it still predicts better the branches which will prune. The best is n consistency. If you pass n consistency, you will guaranteed not backtrack. So, which one is better? Why not n consistency all the time? By the way, we don't use n consistency. Two or three consistency is usually used. So, it goes like this, that I had an algorithm which without heuristic was d to the power of n. This is backtracking. I said I'll not reduce this complexity, but I'll apply two consistency, three consistency, four consistency, and that will add something to my prediction capability. So because I added two consistency, three consistency, my algorithm actually has a complexity of whatever is needed by backtracking with all the heuristics. So this is the worst case, not the average case, plus the complexity of consistency check. And because you apply it for all of them, so it's actually multiplied. Now, what really happens around over here, for 2 consistency, this of course takes a time of c times d cube, but then it significantly reduces this. The prediction is a lot better. In case of n consistency, this virtually vanishes off. I don't have an exponential over here, so this becomes almost a constant, but making a graph, checking for n consistency is itself d raised to power n operation. So there is a trade-off between, and I keep on saying it, I said that in A star, I said that in Edwards aerial search, I'm saying that again. There is a trade-off between how much time the heuristic saves and how much time is needed to calculate the heuristic. In this case, heuristic is boom. It saves you so much of time that exponential becomes linear. However, the heuristic is exponential to calculate. Does that make any sense? No. So, and it's making calculation the heuristic is so expensive that you would have solved the backtracking algorithm itself within that time. So the heuristic is making the time absolutely go away of the actual algorithm, but the heuristic is taking an exponential time, and therefore you settle for 3 consistency. Now, if you heard this question before, then yes. Why quicksort divided into 2? Why not divide them into 3, 4, or 5? Merge sort, why divide into 2, not 3, 4, 5? Binary search tree, why 2 children? Why not 3, 4, and 5? It all goes to the same thing. How much time do you save versus how much of computation per node do you incur? Both the extreme cases are bad. So, let me give you another strong definition which has a lot of utility, and it is called as strongly k-consistent. A graph is strongly k-consistent if it is 1 consistent and it's also 2 consistent, and it's also 3 consistent, and it's also 4 consistent, and all the way up to k consistent. Now, the interesting thing is that suppose you make the graph strongly n consistent. Suppose your constraint graph is strongly n consistent. Something wonderful happens. You never backtrack. No matter what you do, you never backtrack, because you can always take a value of v1 and because you can always take in a value of v1, it is strongly 2 consistent. For whatever value of v1 you take, there exists a value of v2. It's strongly 3 consistent as well. For whatever value of v1, v2 you take, there is a value of v3. It's strongly 4 consistent. For whatever value of v1, v2, v3 you take, there is a value of v4. It's strongly 5 consistent. For whatever value of v1, v2, v3, v4 you take, there is a value of v5, and so on. Do I ever make it strongly inconsistent? No. Because to do this, all the time that you require is, now for vi, you have to check constraints for, you still have to check for the constraints. So there is one value possible, but you have to find which of the values in the domain is possible. So for vi, you will have to check constraints with V1, V2, all the way up to Vi minus 1. So you'll assign a value to Vi such that it is consistent with V1, V2, all the way up to Vi minus 1. Strongly I consistent means one value is possible, but that still needs to be found out. In the worst case, it will have constraints with all of them, and all of them need to be checked. So basically, I need to check for I values around over here. And to choose a value, I need D. So you have a submission of D, which turns out to be a n squared D complexity algorithm just there. So it's solvable, it's polynomial. However, the complexity to make it strongly n consistent is unfortunately D raised to power n. So this is given n strongly n consistent. How much time do you require to solve it up? And this is the time to make it strongly inconsistent. And you see that this is where the lacuna is. Time to make it strongly inconsistent. And this is basically given that my graph is strongly inconsistent. Time to get a solution. So if you think about this, it's okay, but the lacuna is over here. So you could still make it strongly 1 or 2 consistent, but you could make it strongly 2 or 3 consistent, but not more than that. There are other consistency checks that I'll not really talk about. Like for numerals, you have consistency checked based on bounds. So I say V1 plus V2 plus V3 is less than equal to 10, and somewhere I get V3 can take in values which are 5, 6, 7, 8, 9, 10, 11, 12. So of course you have two things, that it cannot take in values which are 11 and 12, and V1 can now only take in values which are 0, 1, 2, 3, 4 and 5, because the moment it becomes 6, this constraint is violated. You also got in something which are resource constraints, so everything needs a minimum resource, and because everything needs in what is a minimum resource, therefore, what you do is that you sum up as per the current domains, as per the current readings, the least resource required by every domain. Is it larger than the resource that you have? If it's there, then you can say it's not possible, which is exactly the same problem which is related to your bounds. For all differences case also, you've gotten similar issues, that you delete all the variables which have values, then say how many variables you have, how many values that you have. If all the variables need unique values, script arithmetic, then at least number of values should be greater than equal to number of variables. If that's not the case, then again, it's good to delete everything up. It's good to say that it's not possible. And therefore, what really you'd be doing is that you'll be just applying 2 or maximum 3 consistency. The higher consistency you apply, the greater predictive capability you have, and the lower consistency you have, the lower predictability you have. The caveat is the time required to make the graph as consistent at the very first place.